Hi everyone. In physics, there are a number of key physical concepts that very regularly show up when analyzing different kinds of systems. Things like Newton's laws, or conservation of energy, or conservation of momentum, not to mention a host of different mathematical methods for applying these concepts. Very often, the same physical system can be analyzed using a variety of different methods. But it's helpful to consider which methods and concepts will be most helpful for a given scenario. This is one of the things that makes most physics courses very different than most math courses. In a math course, you're generally given an equation with some unknown, and you're asked to solve for that unknown. Whereas in a physics course, you're generally given a physical scenario, some kind of system, and you need to figure out what equations we can use to accurately describe that system and how that system will evolve. And that involves identifying which physical principles will get us those equations that we need to solve for whatever property of the system we happen to be interested in. So in your typical college level introductory physics course, you'll generally go through some of the following topics. For example, you'll talk about kinematics, we can talk about Newton's laws or dynamics, we can talk about conservation of energy or conservation of momentum, and sometimes conservation of angular momentum as well. These are generally things that are introduced in a one-term or two-term college level introductory physics course. Again, plus or minus some other topics, depending on the exact course. And I want to emphasize that this is certainly not an exhaustive list of all key principles that come up in physics. For example, in thermodynamics, in addition to conservation of energy coming up a lot, we also need to consider concepts of entropy and other concepts in statistical mechanics. In special and general relativity, well, obviously, we have the principles of relativity coming into play, where the outcome of an experiment should not depend on the choice of coordinate system or the frame of reference of that experiment. If I'm moving in a certain frame of reference, I should be able to do all of those experiments and get the same outcome. Quantum physics has its own set of principles, which we're definitely not going into here. I'd love to, at some later point, make a playlist on properties of quantum physics, but again, that's not going to be for now. But even this starting list of kinematics, Newton's laws, conservation of energy, conservation of momentum, and conservation of angular momentum allow us to predict how a wide range of systems is going to evolve over time. Now, all of this is great, but we do need to be very careful in identifying how each of these principles are applied and under what conditions each of these principles is going to be most useful. It's like if you're to build something and you have some set of tools. You have a saw, a hammer, a drill, a lathe, a whole bunch of different pieces of equipment, and each of these tools is going to be helpful to you. But each of those tools is going to be helpful in a specific kind of situation. And we need to know which tool is going to be right for which kind of job. And the same thing applies to when we're looking at these key physical principles and when we're going to apply them. It takes a lot of practice to learn how to do this, and I'm not going to be able to summarize the entire thing in one video. But let's start by very briefly going over each of these concepts to see if we can find some general hints regarding when each of these methods is going to be most useful. So let's start with talking about kinematics. Kinematics is basically just describing the motion of objects. So if I have an object that's kind of moving around, we can relate the position of that object at any moment in time, the velocity of the object, the acceleration of the object, and again, how all of those are changing with respect to time. Well, if we're going to be describing these things and using these terms, we had better define them. So velocity is just a measure of how is your position changing with time. In these equations, this triangle symbol, this is something that we see a lot in physics. This is the Greek letter delta, and it just represents the change in some quantity. So if I'm talking about my change in position, that's going to be my final position minus my initial position. How is my position changing? And we're dividing that by how much the time changed. What was my final time minus my initial time for that particular interval? If we go with the calculus version of this, we can say that the velocity would be if I took a time derivative of my position function. So again, derivatives talk about how something is changing with respect to something else. In this case, we're saying how is my position changing with respect to time. So we can use calculus as a tool to calculate these velocities. We can also look at acceleration. Acceleration is defined as how is my velocity changing with time. So again, we've got this change in velocity, final velocity minus initial velocity, divided by the change in time. And again, there's a calculus version of this. We can say the acceleration is the time derivative of my velocity function. So it's how is my velocity changing with respect to time. And these accelerations would tell you by how many meters per second is my velocity changing each second. So that's where we get the acceleration units of meters per second squared from. Now, in the case where we have a constant acceleration, where both the magnitude of that acceleration and the direction of that acceleration is constant, then we can derive a set of equations to look at how my position is changing with time. So if I know my initial position, the little subscript 0 represents just initial values. So if I have my initial position and my initial velocity and my acceleration, if I know what time I'm interested in, I can figure out, oh, where is that object located? What is its position? Same thing for velocity. If I know what my initial velocity is and this constant acceleration, at any other time, I can plug in a time and say, this is what the velocity of the object is going to be. And then again, there are variations where we can take other combinations of these terms. So if I can relate my final velocity to my initial velocity, the acceleration, and how much my position changed. But again, this set of equations works in the case where we have a constant acceleration. But if we don't have a constant acceleration, if that acceleration is changing in either magnitude or in direction, we have to be very careful because these equations will not work. These equations are derived under a certain set of assumptions. And if those assumptions are not valid, then we can't have confidence in these equations, again, for those cases. Let me give a couple of examples. Suppose I have projectile motion. So I throw an object and it moves through the air. If we are on or near the surface of the Earth, and gravity is the only significant force, so we're saying air resistance is negligible, there aren't any other things that are pushing and pulling on the system, then gravity will cause this object to have a constant acceleration. And when dealing with projectile motion questions, I've had a lot of students in the past say, well, I'm going to throw the object, and when I catch the object, well, it's now no longer moving, so its final velocity should be 0. But that's inaccurate because the second I touch the object, the second it reaches my hand and I catch this object, it's no longer satisfying those assumptions of gravity is the only significant force acting on it. What we should be saying instead is, I can use these constant acceleration equations, and the acceleration due to gravity, which on or near the surface of the Earth is 9.8 meters per second squared going straight down. So again, during that motion, if gravity is the only thing acting on it, that acceleration has the same magnitude and is going in the same direction. That's going to be the acceleration from the moment after it leaves my hand to the moment before it reaches my other hand. So during that segment of the motion, not once I catch it and not as I'm throwing it, but just during the segment of the motion where I am not in contact with the object, that's when I'm allowed to use these constant acceleration equations. So we have to be careful of when these equations are valid. Another example would be uniform circular motion. Let's say I have an object that's moving in a circle at a constant speed. Well, you can show that since the direction of that object is changing, the direction that that object is moving in, its velocity direction is changing, it is still accelerating even though the speed is constant. And that acceleration, if this is going in a circle at a uniform speed, that acceleration will always point towards the center of the circle and have a magnitude of that speed squared divided by the radius of the circle that it's moving in. Now you might say, well, if the speed isn't changing and this is moving in a circle of constant radius, v squared over r, that should give you a constant acceleration. So can't we use these equations? And the answer to that one is no, because the direction of the acceleration is always pointed towards the center of that circle. So as it moves, the direction of the acceleration is changing. So again, these equations would not be valid under that particular set of conditions. So again, if we do have a constant acceleration, we can use these equations. But if not, then we have to go back to some of these other more fundamental concepts and say, well, I have to calculate more specifically, how is this direction of acceleration changing, or how is this magnitude of acceleration changing? We have to be a little bit more careful with how we apply those concepts. Let's talk about Newton's laws next. So Newton's laws say, I want to be able to identify what causes different kinds of motion. So this is going to relate forces, interactions between objects. Gravity is the earth pulling down on me. If I have air resistance, it's air pushing against my hand as my hand tries to move through the air. If I have friction, it's those two surfaces rubbing against each other. They're all interactions between different objects. And Newton's laws takes those forces and relates those forces to how is the motion of the object going to change? What is going to be the acceleration of that object? So this is Newton's second law, at least Newton's second law in the case where the mass of the object is constant. There's a little bit more of a fundamental version of this, but if the mass is constant, then we can use this equation. So the key idea here is that if I can add up all of the individual physical forces acting on an object, and those forces are acting on an object of a certain mass, that's going to cause this object to have a certain acceleration. The higher the mass, the lower the acceleration is going to be. Mass is an object's resistance to acceleration. And the direction of this net force, the sum of all these forces, that's actually going to match the direction of the acceleration, since, as far as we know, the only masses that we know of are positive values. Okay. So what we can do with this is identify that there's lots of different kinds of physical forces. Again, things like gravitational forces, normal forces, spring forces, pressure forces, just many, many different kinds of forces. And the key idea is that if I know what the forces acting on the object are, I can determine something about the motion of that system. I can figure out how that system is accelerating at that particular moment. And vice versa, if I know about the motion of an object, I can work backwards and figure out something about what forces are acting on that object. This is used in a lot of different cases. For example, let's say I observe a star, and stars usually are going to be orbiting around the center of the Milky Way, the center of our galaxy, or the center of whatever galaxy they happen to be in. But usually those stars would follow a straight line. But let's say I see that star wobbling a little bit. Well, I might not be able to see the planet that's orbiting around it, but if I can measure the properties of that wobble, and I know how that system is accelerating, I can figure something out about the gravitational influence of whatever unseen planet is acting on the object, and I can start figuring out some of the properties of that unseen planet. So again, this is used in a lot of different situations, and another thing that we can do with this is, if those forces acting on the object are constant, then we're going to have a constant acceleration. And if I have that constant acceleration, same magnitude of acceleration and the same direction the whole time, I can go back and use my constant acceleration equations from the kinematics part. Now, we can also have cases where the forces might be changing as the object moves from one location to another. And if those forces are changing, well, the situation becomes a lot more complicated. At every one of those different instances, every time that force changes, my acceleration is going to change as well, so we won't be able to use those constant acceleration equations. Well, maybe there's a better method in the case where those forces are changing. And that kind of leads us to conservation of energy. If I have a case where my force changes with position, let's say I have a spring, and as that spring either compresses or stretches, the amount of force that that spring applies is going to be changing. So if I have a spring and I compress the spring and I'm using it to launch an object, as that object moves, at every time that object moves and the spring changes how stretched or compressed it is, those forces are going to be changing, those accelerations are going to be changing, which means I could either keep on recalculating what those new forces are, keep on recalculating what those new accelerations are, how that affects the motion of the object, or maybe there's a better method. Okay. In conservation of energy and some of the other topics we're going to talk about, we want to be able to identify quantities that are conserved in a closed system, where no matter what that system happens to be doing, these particular quantities are staying the same. And that makes them much easier to use and much easier to apply to different kinds of situations. So we can introduce these concepts of work, the work done by a force, so how much energy is added by a force, where that work done is equal to the force times how far it moves times the cosine of the angle between the direction of the force and the direction that the object is moving in. We can talk about different kinds of energy, like kinetic energy, the energy associated with the bulk motion of an object, gravitational energy, the higher up in the air an object is, the more gravitational energy it has. This is the equation if you are on or near the surface of the Earth. If you go far from the Earth, it's going to be a different equation. We can talk about how much energy is stored in one of those springs, which depends on the spring constant and how stretched or compressed that spring is squared. And again, there's many, many other different kinds of energy. But the key idea here is that energy can't be created or destroyed, but we can change it between different types. So I can have an object that starts with gravitational energy, and when I release it, it falls downwards, and as it falls downwards, that gravitational energy gets converted into kinetic energy, the energy of motion. So the further the object falls, the faster that object is going to be moving. And depending on the situation, this can greatly simplify the algebra. Again, think of the case where I'm using a spring to launch an object. If I was to try to use Newton's laws, again, when that object is being launched, at every little moment, every little change in the stretch distance of that spring, those forces are going to be changing, those accelerations are going to be changing, and it's going to be very complicated to calculate how the motion of that object is going to change. But with conservation of energy, we can just say, well, if I have this spring and I compress it a certain amount, I can calculate how much energy it starts with, how much potential energy it starts with. When the spring launches that object, well, that spring energy is being converted to kinetic energy. And since energy can't be created or destroyed, I know that whatever spring energy I started with has all been converted into kinetic energy, and I can figure out how fast that object is going to be launched at. In a lot of systems, if we're talking about looking how a system changes over an interval, I go from some initial state, the object compressed on the spring and ready to launch, to some final state, well, the spring is now uncompressed and the object is being launched. We can use that to, in a lot of cases, very, very greatly simplify the algebra. But we again have to be careful with how we use this tool, because we can only use this if we're considering a closed system, so we can keep track of if any energy is being added from external sources or leaving to external sources, and also make sure that we are properly identifying all of the different types of energy that are present in the system. So again, we still have to be careful with how we are applying these ideas of, in this case, conservation of energy. We can also talk about conservation of momentum. The definition of momentum is that momentum is just the mass of an object times its velocity. It's a vector quantity, so we do have to be careful about direction. And this definition of momentum, again, has some very, very useful properties. One of the key ones being, if I have a system where there are only internal forces, so let's say two objects run into each other and bounce off of each other, there's going to be a force between those two objects. As long as there are no other external forces, and it's only internal forces, the total momentum that I start with before the objects hit, and the total momentum that I have after the objects bounce off of each other, that's going to be conserved. This is ultimately a consequence of both Newton's second and third laws going together. Newton's second law, you can use that to figure out how your momentum of one object is going to change if a force is applied. And Newton's third law is if object A is pushing against object B is applying an equal and opposite force to object A. And since those forces are opposite, you're going to get exactly opposite changes in their momentas, so the total momentum of the system will be conserved. It's just one object transferring some of its momentum to the other object. This is extremely helpful if you're analyzing things like collisions or explosions. Again, any system where all of the forces are all internal to the system. So again, collision, during that collision, the interaction force between those two objects is almost certainly going to dominate over any other forces that are acting on them during one of those brief but intense collisions. Same thing for an explosion. An explosion, those objects are going to push off of each other. If I look at that system and it only has internal forces, I can use this conservation of momentum idea to great effect. So, as an example, let's say I have a one-dimensional collision between two objects. So two objects that are moving towards each other, they hit each other and maybe bounce off a little bit. We can look at the total momentum before, saying object 1, its mass times its initial velocity, plus object 2, its mass times its initial velocity. Well, after, if I track the motion of both objects after, we've got the motion of object 1, mass of 1 times its final velocity, plus mass of object 2 times its final velocity. And in any collision, this equation has to hold. If it's a collision where there are only internal forces, this total momentum before the collision and after the collision must match. But this isn't actually quite enough information to fully describe what's going to happen to this system. It's an important constraint. It definitely is involved in the calculation, but right now we would have one equation with two unknowns, the final velocity of object 1 and the final velocity of object 2. So we can't take one equation that has two unknowns and unambiguously solve for both of those unknowns. We need some additional information in order to fully use conservation of momentum. And this generally comes, for objects running into each other, this generally comes from energy considerations. Are we dealing with an elastic collision where they're bouncy objects and the total kinetic energy is also conserved as they bounce off of each other? Is it an inelastic collision where they lose a little bit of kinetic energy but can still move off of each other? Is it completely inelastic where the objects just stick together after the collision? Well, that has to do with whether or not energy is conserved. So again, conservation of momentum is a very important physical principle, but for things like collisions, it's not the only thing. We can't get away with just using conservation of momentum and nothing else. We also have to know, how is kinetic energy being conserved? Do we have an elastic collision or an inelastic collision or something else? The last one that I want to talk about is conservation of angular momentum. Now, this one is a little bit less familiar, so I'm going to try to go through this fairly briefly, but it's going to come into more play when we in future videos. So, angular momentum, the definition of angular momentum is basically a measure of how much stuff is rotating around a certain axis. Okay. So a form that's going to be a little bit easier to kind of understand what it's talking about is this form here, where the angular momentum is equal to something called the moment of inertia, which is a measure of the mass of an object and how that mass is distributed around some rotation axis. So if I'm rotating on this chair, if I'm spinning around on this chair and there's an axis that I'm spinning around, my moment of inertia is going to depend on my mass and how far from the rotation axis that mass is located. In fact, it depends on the distance from the rotation axis squared. So if I take some of my mass and move it further from the rotation axis, I hold my arms out, well, that's going to significantly increase my moment of inertia. So we've got this moment of inertia, and we've also got this term, which is the angular velocity. How rapidly am I rotating? How many, technically it should be radians do I rotate through per second, but you can think of this as like revolutions per second. How often am I spinning? And if I have a system where there are only internal torques, there are no external torques that are going to change my rotation rate, then in those cases, the total angular momentum of the system is going to be conserved. The quintessential example of this would be a figure skater spinning around and then quickly pulling their arms in, which causes their rotation rate to increase. In this case, we're saying the angular momentum is staying the same. My moment of inertia times my rotation rate is staying the same. When the figure skater is spinning with their arms out, they have a very large moment of inertia. When they pull their arms in, that's going to lower their moment of inertia. But if the angular momentum isn't changing, that means their spin rate, their angular velocity, has to increase. And again, for systems where we have only internal torques, there's no external torque acting on the system, we can say that this total angular momentum is going to be conserved. And again, it's a very useful tool under these particular conditions. Another example of this would be if a system is rotating on a hinge. So let's say I have a lever that's rotating on a hinge. Again, if there are no external torques acting on the system, then the angular momentum, the total angular momentum of that system will be conserved. And for the case of a lever, let's say there are some forces acting right on the hinge. Well, if I measure my angular momentum around that hinge, any forces that act on the hinge aren't actually going to produce any torques. Think of trying to open a door by pushing right on the hinge of the door, right on the rotation axis of the door. If you're pushing right at that rotation axis, it doesn't produce any torque. Same thing for this lever. If I apply some forces right at that hinge, it's not going to apply any torques to that system. So that system will still have this conservation of angular momentum, again, around that particular hinge. So with all of these examples, again, our goal is to say, if I have a certain physical situation, a certain physical system, and I want to analyze its motion and be able to predict its motion, we have a set of different tools. We've got kinematics describing motion. We've got Newton's laws relating forces and accelerations at a particular moment in time. We've got conservation laws, things like conservation of energy, conservation of momentum, conservation of angular momentum. And each of these tools is useful in a certain set of circumstances, in a certain set of physical conditions. So when we're approaching different kinds of physical systems, we want to be careful of which tool we're using and making sure we're using not only a tool that will get us the right answer, because again, if I try to use angular momentum and conservation of angular momentum when there's an external torque, I'm going to get the wrong answer. But even when we're using these appropriately, we want to find what is the easiest way, the least error-prone way of reaching a good conclusion, a conclusion that we can have a high reliability in. And then, of course, as always, in any kind of science, we want to test these ideas. So we're going to see some examples of this when in an upcoming video where I talk about the lever experiment that I'm going to be finishing up, talking about how we can make predictions using things like conservation of angular momentum and conservation of energy for this lever system. And then eventually we are going to be putting that to the test. So those are some of the things that are going to be coming up. As always, if you have questions or comments, please throw those in the comments below. I'm always happy to try to respond to questions that are in there. And otherwise, have a good rest of your day.